Hello everyone, welcome to MRU E-Learning powered by Malla Reddy University. I am Sanabam Binesh Singh, Assistant Professor, AIML Department. So today I'm going to talk on the topic Introduction to Language Processing System with Compiler Fundamentals. It is one of the fundamental topic in computer science that will understand how a computer understands the program written by the human being. So understanding this process will help not only in compiler design, but also in operating system, in programming language, as well as in modern AI framework. So these are the agenda of my today's presentation. So it will include introduction to language processing system, overview of compiler, structure of compiler, and phases of compiler. So the first is, what is a language processing system? So to understand it, let's first try to understand why and what language refers to. So when we say language, it is nothing but a medium of communication, right? So if we have two person or two entity, let's say person, the way of communication is language. So if they have the common language, there is no issue in the communication. What about a situation where one person understands only English and another person understands only Telugu? So in that scenario, whether the language acts as the communication medium? No, right? So we need a tool that will convert one language to another, right? So to communicate between those two persons, we need a tool that will translate one language to another. So in the same scenario, if we take the entity as human being and computer, we also need a tool that will convert the language from one to another to make a proper communication. Okay. So if we come to the system, a language processing system can be treated as a system that translates program written in one language to another. It will usually convert high-level language into machine understandable form. And this system may include tools like preprocessor, compiler, assembler, linker, and loader. Then the next is, as I said, humans usually understand high-level programming language or our natural language, which are convenient and easy to read and write to human being, whereas computer understand only machine language. In the sense, they understand only binary numbers. So there is no direct communication when we are talking about this language. So there is a communication gap between human and computer as we are convenient with two different languages, right? So this language processing system will act as a bridge between this programmer and computer hardware, where it will convert the high-level language that are comfortable to the programmer to the low-level language that is being used in the machine itself. Okay. If you look at the structure of a language processing system, usually it might consist of these different tools. So first, we will have a source program, where the source program will go through the first tool, that is preprocessor. So preprocessor will handle the directives and macros, and it will give a modified source program, where this source program will go to compiler and it will convert this source program to the assembly code, where assembly code will be again will be put into another tool called as assembler, where it will convert this assembly program into relocatable machine code or object code. So whatever program we give, usually it will be divided into different pieces. So that's why we have relocatable small pieces of object codes. So those codes will be linked together by linker. So the tool linker will link all those object codes, and once it is linked, it will be loaded to the memory by loader. Okay. So loader will load the object code to the memory, and it will execute and will give the target machine code. If you consider it with the example of C program running on a host machine, what we are doing is we will write the program in C, that is a high level language. So this C compiler translates the program into assembly code. Then assembler converts the assembly program into machine code or object file. Then the linker will link all object files and libraries to create an executable file. The loader will load the executable into memory, and then the program will be executed by the system. The next is about the compiler or the overview of compiler. When we say compiler, it is nothing but a tool that converts one language to another, or it is a language processor that translates a program written in a source language into a semantically equivalent program written in an target language. So it will translate the entire source program into a target machine program. So it will generate an executable file before program execution. It will report errors after compilation is completed. So here we will give a source program to the compiler in one language. Compiler will convert it into a target program. If it finds any errors, it will return the error. So the target program then can be given some input. Accordingly, it will give an output. Next is the structure of a compiler. Coming to the structure of a compiler, we can divide the structure of compiler into two parts. First, we call it as analysis part, and another as synthesis part. Or the another name for analysis can be termed as front end. Another part of synthesis can be called as back end part of the compiler. So what does this part do? So for example, if we are talking about analysis part, as the name suggests, analysis, it's going to analyze the lines of code. So it will break down the source program into components. It will check syntax, semantic, and it will generate an intermediate representation. If there is any error, there will be reporting of that error. So in this analysis part, it will just analyze the given line of code, and it will report any error if. And in the synthesis part, whatever that we have from analysis part, we will have an intermediate representation. Along with it, we have a data structure called symbol table that will have some information. So with the use of this information, we will try to generate the equivalent machine code of the given source code. So we will make use of our symbol table and the intermediate representation to generate our final target machine program or machine code. Coming to the phases of the compiler, we can divide the compiler phases into 6 phases. The first being as lexical analysis, second syntax analysis, third semantic analysis, fourth intermediate code generation, then fifth code optimization, and sixth code generation. So here first we will give source code. It will go through this 6 phases of compiler, then it will give the equivalent machine code of that particular source code. So every phases are associated with a data structure of called symbol table. Then there will be an error handling part as well. Coming to the analysis part of compiler, as I said before, we have divided the compiler into two parts, analysis and synthesis. When we talk about analysis part, it will consist of the first three phases. So the first thing is we will give a source program to the first phase, that is lexical analyzer or lexical analysis, where it will go through all those characters and it will return the output as tokens. Then syntax analyzer will take those tokens and will create a tree structure called as syntax tree or parse tree. Then those syntax tree will go through semantic analyzer, where it will check the semantic correctness and it will update the syntax tree or the parse tree. So if we discuss in details, the first phase of the compiler is lexical analysis or lexical analyzer. So it is also called as scanner or scanning. Okay, so lexical analysis phase is also called as scanner, as it scans the stream of characters. So it will scan the source code as a stream of characters. Then it will group those characters into a meaningful lexemes. Those lexemes are being converted to tokens. So which is nothing but the output of the first phase, lexical analysis phase. So here we will also remove white space comments in the source program. So tokens are nothing but those basic units such as identifier, keywords, operators, constants. So those are the tokens that will be given as the output by the first phase of compiler. So these tokens are usually represented as in the form of token name along with an attribute value. So token name, it might be identifier, attribute value, it will be one value that will point to the symbol table. So if we take an example over here, so we have a line of code over here. So we have a line of code over here. What lexical analysis is going to do? So it will start scanning from left to right. It will start scanning from here. Then it will get an identifier over here. So it will return as a token over here. So as I said, we'll have token name and attribute value 1. It means the identifier 1 has been saved in the symbol table. Then similarly for the second one as well. Similarly for the third one as well. So it will keep on going till the end of the code. So what we have to understand is in lexical analysis phase, whatever lines of code we give, we will be written with tokens as a output. The next phase of the compiler is syntax analysis phase. It is also called as parsing or parser. So it will take token from the previous phase, that is analysis phase, as input, and it will check it against the grammar, language grammar. It will ensure that it is syntactically correct. So it will use context-free grammar and it will generate syntax tree or parse tree. If there is any syntax error, it will report it, like syntax error like missing symbol. If we look at the example, so this is what we have from the previous phase, that is lexical analysis phase, those tokens. So those tokens will go through the syntax analysis phase, so where it will convert in the form of trees called as parse tree or syntax tree right. So here the leaf nodes of the tree will represent the, here all this leaf represent the operands, whereas the inner or the interior node represents the operators. So all those operators will be in the inner nodes. Then comes the next phase or the next that is semantic analysis phase, which is nothing but the third phase of the compiler, where it will use the syntax tree that is generated by the previous phase and the information from the symbol table. So the main aim of this particular phase is nothing but to check the correctness of its semantic. So semantic consistency will be checked over here. Here it will ensure that whatever identifier we use, it has been declared. Then it will check the type compatibility of the variable that are used in assignment and expression in the lines of code. So it will perform type checking to ensure that operators have valid operands. For example, if we look over here, this is what we have from the previous phase. Suppose if we look at the first line of code, we have this tree variable, right? We have this tree variable. If we declare it as float variable, but we have a value over here as 60, which is an integer value. Here there is a type mismatch, so there is no compatibility. So in this case, semantically it is wrong, right? So we need to make some correction. What correction we do? We do type conversion. So in this phase, we do type checking, then we do type conversion so that there is no issue. So we will convert our integer value to float value so that it can work with other variable, right? So we have the float variable as the other identifier. The next, that comes to the end of the analysis part. So with every part, we know that symbol table is associated. So what is symbol table? Symbol table is nothing but a data structure that is used by the compiler, where we store records of the identifier. So it may include the name, type, scope, location, etc. So it may look like this. So symbol table may look like this, where this is the attribute value, where we discuss that an attribute value will be associated with the token. So 1 represents the attribute value, where it will say all the details about that particular identifier. Similarly, for all the identifier, it will save all the details in this symbol table. Next comes to the part of synthesis part of the compiler. So far we have generated first tree. We have the information in our symbol table. Then using this symbol table and first tree, we are going to first go through the intermediate code generation or generator, where it will generate an intermediate code, which later will go through code optimization, where it will optimize the intermediate code. Then it will go through the code generation, where it will generate a target program of the source program. So let's see the next, that is intermediate code generation. So in this phase, we are trying to generate an intermediate code of our given source code. So we have a commonly used intermediate representation called as tree address code that I'll discuss in the next slide. So it uses an assembly line instruction, where it has an instruction where each instruction has at most 3 operands, and the operands act as a temporary registers, and it will make optimization and code generation easier. So here is the example. So this is what we have from the previous phase. So in intermediate code generation, it will generate an intermediate code like this, where we have temporary variable, and we have used this as tree address code representation. So this above first tree has been represented by tree address code in this intermediate representation. Then we have code optimization. So this code optimization will try to improve the intermediate code so that we can have a better target code. So what do you mean by better? It may be faster, it may be shorter code where the target code will consume less power. Okay, so if we take the previous example from the previous phase, this is what has been generated by intermediate code generation. Now by code optimizer or code optimization, it will try to reduce the line of code. These 4 lines of code can be replaced by these 2 lines of code, right? So as we saw that first what we did was nothing but conversion of our integer value to float. Then we do the multiplication part, then addition, then finally we assign the value to the identifier. So these 2 lines of code, they do the same thing, but we just optimize it. So here also same thing, that we have do the multiplication part with the identifier, we save it in our temporary variable t1, then we add the value with the identifier and save or assign it to identifier 1. Okay. So in short, we just try to reduce the number of lines of code. And here comes the final phase of the compiler, that is code generation. So here it will take the optimized intermediate code as input. It will map the intermediate code to the target machine language, and it will convert it into a machine instruction, where machine instructions are usually relocatable, and it will ensure that the correct execution on the target machine. So let's see with the example. So this is the example what we have. If we remember it, so this is what we have from the previous phase, and if you look over here, this is the final assembly code that represent this optimized code. Okay, so what does we do here? First, we have load f for float. So since we are dealing with floating point, we have f in the instruction. So load f. So first is load f, right? So we are loading identifier 3 to the register R2. Then in the next operation, first we are done with this. Then in the next operation, we are doing this multiplication. That is, R2 contains the value of our identifier 3. It will multiply with 60. Then it will store the value in R2. And next, so we are done with this part. Then next we are loading identifier 2 to register R1. Okay, so we're talking about this. Then now R2 represent this line of code. R2 represent this line of code. Then R1 is this one. Then we have what operation over here? So it is nothing but the addition of these 2 terms. So R1 and R2 will be added, and it will be stored in R1. Lastly, we store the value of R1 to the identifier 1. So we store this value in the identifier 1. Okay, so this is the equivalent final assembly code of the given source code. Okay, so with this we have come to the end of the session. Thank you.